Welcome. In this session, we'll explore the hidden layer of our simple artificial neural network. We'll derive this for only a single input. So our input for this will be some data 1 form, and this will be the input to layer 2 because that's how we're working. The input layer is layer 1, and then the hidden layer is layer 2, and we'll use the same activation. Now it's prescripted by 2 for each neuron. And what we'll do here is we're now going to say, how do we deal with a data observation coming in to a layer of neurons? So the way that we'll start this out is by saying that we'll say for neuron J, neuron number J in layer 2, what we have is the linear response in layer 2 for neuron J is we take the data 1 form, we augment it with a 1, and then we multiply it by the weight vector layer 2 for neuron J. So if we have, for example, 2 neurons, these 2 neurons will in general have distinct weight vectors. So we'll gather these into a weight matrix. So what we'll do is we'll say that the weight matrix for layer 2 is, if it's just 2 of them, it will be weight vector layer 2 number 1, weight vector layer 2 number 2, and I'll put some dots there, but we'll actually only work through 2 neurons here. And that gives us a weight vector for layer 2. Is what we do is we vectorize that matrix. So that vectorization would be we take the layer 2 neuron 1 weight vector, the layer 2 neuron 2 vector, and we stack them vertically. So now what we can do is we can gather all the linear responses into a 1 form, and we can also think of it as a vector. So what that will be is that the 1 form for layer 2, and I'll draw, so that is a function of the weight matrix and takes into account the observation. So that will be equal to, here it's just what we'll do is we'll take the observation and multiply it by the weight vector. So that will give us a 1 form. And we could transpose that, so that's equivalent to saying that the vector is, if we transpose this, that would be W2 transpose times the X2 data vector 1. So this is, again, we're transposing and we're using 1 forms and vectors for whatever is convenient at the time. So this is most convenient when we're thinking of data flow, but when we go to differentiate, we really don't know how to differentiate these, so we're going to have to do a little bit of extra linear algebra. The activations, applying the activation function, the activations are, this will be the layer 2 activations, and now we're going to put an arrow over that because it's going to be a function, it's going to be a vector, and that will be, this will be activation for number 1, and so for neuron 1 that is the layer 2 number 1 term, and then it'll be the same activation function, but we'll also apply it to the neuron 2 linear term. So that will then give us the activations. So these then become the inputs to layer 3. So we can think of the layer 3 input. So layer 3 is what we did in the previous session, right? That's the output layer. The layer 3 input is the transpose of the layer 2 activation. So there we have it. And we can finally, I'll put a little bar here so that I can keep track of what I'm doing. We can gather weights. As we can say that the weight vector, the single weight vector for our entire little artificial neural net is, we're going to stack it this way. We're going to stack the top as the output, and next we'll put the hidden layer. So this now lets us find a weight vector for the entire neural network, which is just catenating these or augmenting them. So the residual error, so residual is R, and objective is F3, and that will equal that function G of R. Now R is a vector, so residual is a vector. So the residual is still, sorry, that's still a scalar, and everything else follows. So the objective function now has a gradient that depends on two parts. The gradient will depend on the layer 3 weight vector and on the layer 2 weight vector. So it's actually going to have a simple structure. The gradient of F3 will look like this. It will be a gradient of level of F3 as a function of the weight vector for layer 3 and the gradient for the objective as a function of the layer 2 weights. So that's what we're after. Now, we already know this term. We know the gradient of the objective with respect to the layer 3 weights because that's what we derived in the previous session. This is the remaining term that we have to figure out. Let's see what we can do about that. So the derivative is this. The derivative of the activation function with respect to the linear responses is some Jacobian matrix, right? And we can write that as the Jacobian matrix for layer 2. Now you can see why I wanted to take this observation and transpose it. It's because I have to do this derivative, right? So the input is this, the derivative of the linear response vector with respect to the W vector is also a matrix, but this matrix has a particularly elegant form. So let's observe that this Jacobian matrix is going to be a diagonal matrix. And the reason is that the linear response for neuron 1 does not depend on the linear response for neuron 2. So those diagonal entries are going to be 0. So for a 2 by 2, this is going to be diagonal. And this is going to be not exactly diagonal. It'll have the structure of a Kronecker product. So that will be the identity matrix and the Kronecker product with the data 1 form that we're looking at, which is we take layer 2, augment it, and that's going to be that function. Now, I'm going to spare you the derivation details because this is the differentiation is fairly straightforward, but to mess around with this Kronecker product, we have to use some slightly advanced linear algebra. This is in the written notes for this course, and as I said, I'll just omit that. So the gradient of the objective with respect to the layer 2 weights is, we can write that as the derivative of u3 with respect to x3, put an arrow over that, times the derivative of phi2 with respect to u2 times the derivative of u2 with respect to weight vector 2, and that's going to equal, that will be the weight vector 3 transposed times, and then what follows is this will be the Jacobian for layer 2 cross product with the layer 2 observation augmented. And what will that give us? Well, the steepest descent vector for layer 2 is the negative transpose of this, and now that's with respect to the layer 2 weights, and then we transpose that whole thing, so I'll put some brackets around it, and that will be the minus, now we have to do a little linear algebra, and that will be the identity cross, and now we transpose the observation into a data vector, and we'll multiply that by the Jacobian, and we'll multiply that by the weight vector 3, and multiply that by the backprop term for 3. So the backprop, the back propagation term for layer 2 is the 2 backprop term, that should be a vector here, is the weight vector at layer 3 times the backprop for layer 3. So the steepest matrix is S for layer 2. So remember that when we had a single output neuron, it was a steepest vector. Now it's a layer, so it's a steepest matrix. And this will be, what we'll do is we'll take the layer 2 input, augment it with a 1, and then that gets multiplied by, and here what I did in the notes was I used what's called the Kronecker-Hadamard property, and that works out to be, we take the activation function derivative, so that's a C derivative for layer 2, and we take the Hadamard product, so that's the entry by entry product, with the layer 2 backprop terms, and we transpose that, and then the layer 2 descent vector is minus the vectorization of this matrix, oops, that's a parenthesis, and finally what we get is that that means that the descent vector for the entire artificial neural network is the descent vector for the output layer augmented with the descent vector for the hidden layer, and we now have the descent vector for the whole thing.